Hello, welcome to another video on MR hardware. In particular, we're going to talk about the third part of the RF coils videos. So in the previous videos, we talked about the electronic circuits that are composed of an inductor and a capacitor, and they basically allow natural oscillations as the energy is transferred between the electrical field in the capacitor and the magnetic field in the inductor. The resistance, which is typically the third element, basically provides ohmic losses, and that leads to a dampening of these natural oscillations. The Q value is a measure on how this RLC circuit, how efficient that circuit is. Now, let's say that you have adjusted RL and C to be in resonance with your spins. If you then add a sample to the coil, it will probably change the RL and C of the combined system, and you will need to adjust that to get it back to the right frequency and also to the right resistance. We have talked about efficiency in the previous videos, and mostly about looking at the efficiency of the voltage in the RF coil. However, the more relevant efficiency is actually the amount of magnetic field that you can generate per unit of power. And then, besides the increased efficiency, additional design criteria are the minimization of electrical fields, the spatial coverage of the coil and homogeneity of the magnetic field generated by that coil, and then also other practical considerations like cutout for the eyes and the nose, etc. Bottom line is that most of the discussion today is going to be based on the RLC circuit, but we will refine it, we'll modify it as we need to based on the additional criteria. So we already know that excitation and reception of NMR is based on rotating magnetic fields. And magnetic fields and electric fields are fundamentally linked. In the far field regime, which will come to that, one will automatically lead to the other, and they're really fundamentally linked. Electrical fields are undesirable as they lead to heating in conductive tissues. Now let's look at an antenna, which you can use for amateur radio or radio stations. Those antennas generate electromagnetic waves. In these waves, the electric and the magnetic field components are closely linked. So here's one of those antennas. The electric field lines are in blue, the magnetic field lines are in red. And if we then look at the electrical field profile as a function of distance, or the magnetic field profile as a function of distance, then you can see these kind of antennas are primarily used in the far field regime. And in that regime, which is 10, 20, 30 centimeters away from the coil, in that regime, the electrical field and the magnetic field are fundamentally linked. If you have one, you automatically have the other, and then this wave propagates through space. Now, in principle, you could do NMR with this kind of antenna. However, it will be very inefficient. We like to work in the so-called near field regime, because that is where the sensitivity is much higher. You can see that the B1 field can be much stronger in a near field regime. In addition, you can generate scenarios where the E field is actually much smaller. So even though the B and the E fields are still linked, they are not linked in a 1-to-1 ratio. You might have spatial locations where the E field is low and the B field is high, and vice versa. So as mentioned, RF coils are primarily used in a near field regime because of sensitivity considerations. One of the more popular coils would be a simple surface coil, which would basically just be a copper loop with a capacitor in to basically make it into a resonance circuit. If you then look at the electrical field lines, they are in blue, and the magnetic field lines, they come out of the paper towards us, they are in red. And you can see that you have primarily magnetic fields. However, close to the capacitor there are significant electrical fields as well. Now, one of the design criteria of RF coils is to minimize this kind of electrical field. Now one trick you can do is to basically distribute the capacitors. So rather than having a single capacitor over here, you can split that up into one over there and one over there. And it has a number of effects. For one thing is the magnetic field becomes more symmetrical and more focused. And the electrical field becomes smaller where there's no electrical field at all in the middle of the sample. So by using these kinds of tricks, it is very much possible to reduce electrical fields coming from the capacitors in this way. Okay, let's have a look at the surface coil a little bit further. As I mentioned, it's basically just a single loop with a capacitor in there to make it into a resonant circuit. If we now look at the B1 field, the B1 field basically comes out of the coil and then loops back, down, and then back from the bottom up. And so you can look at the B1 field in the X direction or in the Y direction, and you can see that if you combine these two, you're going to get the B1 field in the XY plane. That's what we're interested in. And you can see that you have the strongest B1 field close to the coil, and it drops off if you move further away from the coil. So surface coils are really good for tissues that are close to the coil. You can also look at it in the XZ plane. In the XZ plane, there's an interesting effect that there is a line where there is no B1 field. At least the B1 field is not useful for excitation, and that is because at these locations the B1 field and the B0 field have the same direction. And as you may recall, B1 needs to be perpendicular to the spins, and therefore they need to be perpendicular to B0. And along this line, that is not the case, and that's why there's a null along these two lines. Now, surface coil is pretty nice, but it's highly heterogeneous, and of course it also doesn't have much signal coverage. So one thing that you can do is basically take that wire and just keep winding it, and until you have a solenoid. You can see here this is a 4-turn solenoid. And the nice thing about this coil is if you would be able to place a sample in the middle, that has a very homogeneous B1 field. So it's very desirable. However, there is a downside to this coil. The B1 field is generated along the axis of the coil, and that means the B0 field then needs to be perpendicular to that. And so if you would bring this into a typical wide bore magnet, you would basically not take advantage of the entire bore. Basically the sample would need to be inserted here and then basically rotate 90 degrees to get it into the center. And so a solenoid is a really good coil, very good homogeneity, very good sensitivity, but it is not very good in utilizing the open bore space. One way to solve that is go for a Helmholtz coil. It's basically a two-turn, two-loop solenoid. It has again a fairly homogeneous B1 field in the middle over here. But it has the advantage that now the sides are open, so the sample can in principle be moved in between the two rungs. Now, there is also a different style of RF coil, and this RF coil uses so-called transverse current density. So in an ideal RF coil, it would be an infinitely long cylinder, and then there would be a current distribution according to a sine or a cosine function. So in it you would have no current on top, then you would have positive current on this side, you would have no current on the bottom, and you would have negative current on the left side, and then back to zero. So that would be your sinusoidal curve. In this case, you would get a perfectly homogeneous B1 field in this direction over the entire length. Now, of course, this is an idealized scenario. This is a continuous current distribution, and it is an infinitely long cylinder. However, there are many coils that try to approximate the sinusoidal or cosinusoidal current distribution. One of them is the Alderman-Grant or slotted tube resonator. You can see this one basically approximates the top of the sinusoid and the bottom of the sinusoid. And so it works fairly well as a first approximation. What I of course forgot to mention is that with this design, now the B0 can be along the length of the tube. So now this RF coil can be placed into the magnet, the subject can be slid in quite easily, the B1 field is downwards, and so you're basically making full use of the open bore of the magnet, and so that's why these are very, very popular. So Alderman Grant was one of the first ones. Saddle-shaped coil is another approximation. Again, it approximated with about 7 or 8 points. And probably the most popular one is the so-called birdcage coil. Depending on the number of rungs that you have, you can get a really, really good approximation. So 16 rungs is pretty standard, up to 32 rungs. And you can see that you really distribute, you approximate this sinusoidal distribution quite well. If the capacitors are in the middle, it is a so-called low-pass birdcage, which is optimized for lower frequencies. If you put the capacitors at the end, then it becomes a high-pass birdcage, and these are better for higher frequencies. So probably the birdcage coil is probably the most popular coil in this group of coils, particularly for medium to low field. These coils tend to be working really, really well. Okay, so let's talk a little bit more about volume coils. So let's say that we have a volume coil given by the yellow circle. Generally, these coils are very homogeneous, and that means that no matter where you are in the object, you're going to have the same receive sensitivity, and you're going to have the same B1 transmit efficiency. So that's very desirable. In other words, the homogeneity is quite good, the spatial homogeneity. However, there is a price to pay. Because the coil is so big, you're going to have lower transmit efficiency, a lower B1 per unit power. And you're also going to have a lower receive sensitivity because, again, the coil is so big. The alternative would be to go for a very small coil, like a surface coil, place it right against the object, and then you're going to have very high signal to noise close to the coil and high transmit efficiency close to the coil. But the downside here is that you're going to have heterogeneity, right? You're going to have high B1 here, but then that is very heterogeneous and dropping down to very low values. Now, the fact that B1 and sensitivity scale in the same way is no coincidence. That has to do with the principle of reciprocity, described in detail by David Holt in multiple papers. Basically, this states that if the transmit efficiency is high, then the receive sensitivity is also high. Or if the transmit efficiency is low, the receive sensitivity is low. They are intrinsically linked for a given RF coil. This is the equation that basically predicts the signal that you detect using B1 for transmission and B1 for reception. Now here, the B1 for transmission and reception is one and the same. However, that is not always the case. So let's have a look at an example here where we have mineral oil at 7 Tesla protons. We have a certain permittivity and a certain conductivity. So those are material parameters. And this is mineral oil. And so like the B1 is quite homogeneous. And here I refer to this as B1 plus because this is the transmit B1. That's the B1 field that is relevant during RF transmission. If we would take that same phantom though, and we would go to switch the mineral oil to water, and all of a sudden we would have a very heterogeneous B1 field distribution, even though the RF coil is exactly the same. We're still at the same field, we just change the phantom. And so this nicely demonstrates that B1 homogeneity is not just determined by the RF coil, it is also determined by the sample that you put in, and it is also determined by the magnetic field that you're working at. So here is a sample water with a high permittivity. And what is happening here is you're basically going to get standing waves in your sample, which is going to basically, if it's constructive, you're going to get more B1. If it's destructive, you're going to get less B1. And so B1 homogeneity is not easy to achieve. Even though the RF coil is perfectly homogeneous, the sample itself may introduce heterogeneity. Now, as I alluded to earlier, during the reception stage, you're going to have a different B1 field that's referred to as B1 minus. However, in these two cases, they are basically the same. And if this is if this is the case, and that's basically true for non-conducting samples, then the equation on the previous slide is indeed true, and the B1 for reception and the B1 for transmission are one and the same. However, things do change if I now add sodium chloride to the water. Now, the sample is going to be conductive, and now you can see that, yeah, you're going to have a different distribution of heterogeneity, But more importantly is that the distribution for the transmit B1, B1 plus, and the reception B1, B1 minus are not the same anymore. And so now, if you want to calculate your signal, B1 plus is no longer equal to B1 minus, and you will need to use the full equation where the B1 plus and the B1 minus are separated out. Okay, continue a little bit more on this. Now let's say we're on a relatively low field, and now we have made a phantom that is a so-called brain equivalent phantom. This phantom with these permittivity and conductivity values approximates the B1 distribution in the human brain quite well. You can see that at this lower frequency it is fairly homogeneous even though it is a conductive sample. You can see there is a small difference between B1 plus and B1 minus, but overall things are pretty homogeneous. If we now move to a higher field, you can see that this is still a brain equivalent phantom, but now you have much more heterogeneity as these standing waves become more dominant. The frequency here is higher. That means that the wavelength of the RF is going to be shorter, and there's basically a better opportunity to basically have a standing wave. People also refer to these as dielectric resonances as well. In this case, you can very clearly see that B1 plus and B1 minus are not the same. Now, this is not just true for phantoms. You can also observe this in vivo. Even at a lower field of 4 Tesla, this is a B1 plus map. And you can see that in the middle you have a hot spot, and on the edges you have a lower intensity. You can already see that here you have more B1 in the middle, there, and less on the edges. So even at a lower field you can already see that. But if you go to 7 Tesla, then you really start to see it. It's well known that if you do just a normal volume coil transmit, you're basically going to have signal voids in the temporal lobes and the cerebellum. And you can see that if you compare the phantom, that would be lobes like this, where you basically almost have no transmit efficiency at all. So this is basically, for a normal single channel RF coil at 7T, this is basically the image that you're going to get. Now, this also has consequences if you're going to design phantoms. If you want to have a phantom that doesn't have this standing wave behavior, you really need to limit the conductivity, because that will lead to these kind of standing waves, and also the permittivity as well, also the size of the phantom becomes important. Right? Again, at higher frequencies, the wavelength becomes shorter, and therefore your phantom the size of the phantom will determine on how much of a standing wave can be set up inside the phantom. And so a phantom design consideration include the size relative to the wavelength, the conductivity, and the permittivity. And so you can either make phantoms that reflect the in vivo situation or that minimize this effect, depending on what you want. Okay, so we now know that we have a fairly heterogeneous magnetic field inside our object, let's say the human head. What can we do about it? Well, the most common way would be to use parallel transmission. So rather than having a single RF coil for transmission, let's break up the RF coil, in this case, in 8 different elements. Each element is attached to its own RF power amplifier. So we can calibrate that. And so here we have B1 transmission maps for each of the 8 channels. So you can see for channel 1, most of the transmit B1 amplitude is below its element, which makes sense. And then for 2, 3, 4, etc., that is all true. However, amplitude is only one aspect. B1 is also, it has a phase component, and you can see on these B1 phase maps that there is a spatial dependence on the phase, but you can map these as well. So what you can now do is, if we just combine these channels as if it was a normal single channel coil, we would get a B1 map that looks something like this. Not very good. The B1 is quite low, so the B1 efficiency is low, it is heterogeneous, there's hotspots there and there, so overall not very desirable. However, now that we have full control over each of the 8 channels, we can do fancier things. So let's say that we're interested in getting good homogeneity over the entire brain in the red ROI. We can then combine these 8 channels in an optimal way, and you can see that yes, the homogeneity is much better, it is pretty much greenish everywhere, but the amplitude is also significantly improved from dark blue here to kind of like yellowish almost everywhere. So this is a greatly improved B1 transmit map. You can go even further if you're interested in, let's say, only a single voxel spectroscopy in the blue circle. You can optimize it over just that, and you can see you can greatly increase the B1 transmit efficiency at the expense that it's lower at other locations, but that's okay for single voxel spectroscopy. So parallel transmission is definitely widely available. It is pretty much standard on 7 Tesla and higher, but of course it is quite an expensive option. Are there maybe some other cheaper options out there? Well, already more than a decade ago, Andrew Webb described one of the first methods, which basically use ultra-high dielectric materials for proton emeride 70. So here you have that same image, where you have these voids again in the cerebellum because of their standing wave behavior at 7 Tesla. And what if you now add ultra-high dielectric materials as little bags at the right location, roughly, you can see that you have a greatly improved image quality. You see all of the cerebellum again, because basically these pads are kind of like steering the B1 and making it locally more homogeneous. Another way to go would be to use universal RF pulses. These are basically specifically optimized to have RF amplitude and gradient modulation. And basically what they do is that if the B1 field have a hotspot in the middle and lower on the edges, these pulses basically achieve a lower flip angle when the B1 is high and a higher flip angle when the B1 is low. It's a bit counterintuitive, but that is the final result. And so you can see that despite the B1 field being very heterogeneous, the flip angle map is quite homogeneous. And one of the oldest techniques is actually using adiabatic RF pulses. Adiabatic RF pulses are pulses that basically work independent of the B1 amplitude above a minimum threshold B1 amplitude. So if you get a 90 degree at a certain B1, you're going to get that 90 degree everywhere. Whereas with a normal RF pulse, you would get a 90 degree here, but it would be only like a 10 degree down far away from the coil. So 10 degree here, 90 degree there, whereas for adiabatic would be 90 degree everywhere. So it's a much better image. So definitely there are some options. Okay, when we talk about RF coils, we have to talk about RF power deposition. Because for every RF pulse that you put into the sample, that you transmit into the sample is basically absorbing a little bit of energy. And if enough energy is absorbed, that may lead to tissue heating, and that can ultimately be dangerous. So this needs to be understood and controlled very well. Now, unfortunately, most things cannot be measured directly and need to be simulated. And so most of these kind of calculations on RF power deposition are done using simulation tools. There are standard human bodies out there for simulation. One is shown here. And then let's say that we're looking at a bird cage coil. So the first thing that you can simulate is, for example, the B1 plus distribution. And that looks like this at 7T and at this at 3T for 1 watt of input power. Now what is important here is that B1 plus is one of the few parameters that can be experimentally measured. So it is very important that the experimentally measured B1 map is exactly the same as the simulated one, because that gives you confidence in the simulations. Right? Most things that follow this point cannot be directly measured and therefore cannot be directly verified. So once the simulation can be trusted, then of course you can also extract B1 minus, which is already difficult to measure. But more importantly, you can calculate the electrical field component. And again, this is the point I made earlier. Here you can see that the B1 is high in the middle, but actually the electrical field is very low in the middle. So yes, they are always present together, but not necessarily in the same spatial location. Here, the E field tends to concentrate in the I region and in the back, both at 3 Tesla and at 7 Tesla. And then using the tissue like conductivity and the calculated E field, you can then basically calculate what the deposited power is. And so now this is a power deposition map, also referred to as a specific absorption rate or SAR map, which basically tells you how much watt of power is deposited per kilogram of tissue for 1 watt of input power. And so you can see that most of the power deposition is on the edge of the brain. And so the guidelines are based on this number. Guidelines from the FDA are 3 watt per kilogram over the entire head for 10 minutes, or 8 watt per kilogram in any 1 gram of tissue. So those are the limits that you can never go above these limits for the human head. Now it is interesting, that the regulations are set for SAR, even though that is not necessarily the most relevant parameter. What is more relevant is actually how much is the rise in temperature. Now, to get to that point, you need to do even more simulation. So you have your SAR maps, and then what you need to have is a bioheat equation, which then takes into account the tissue heat capacity, the metabolic heat generation, perfusion, blood flow, etc., and of course your RF power deposition. And then you can actually calculate a temperature map for a given RF load. And so you can see here that at 7 Tesla, especially around the eyes, you're going to get about a 1 degree Celsius temperature increase in this simulation. At 3 Tesla, that's also where the most increase is, but it's smaller. And of course, the increase is primarily there because it's mostly eyes and skin and bone, things that aren't well perfused. And so perfusion definitely plays a role into this. But again, temperature is also not easily measurable in vivo, and that's why the guidelines are set for SAR. Okay, so we talked about a volume coil. We know that volume coil provides good spatial coverage, but because the coil is so large, it has relatively poor sensitivity and poor transmit efficiency. We also know if we go for a single surface coil, that surface coil has really good sensitivity, but because it's so small, it has poor spatial coverage. Well, can we not combine these two ideas and basically make a volume coil composed of individual surface coil receivers? Well, the answer is of course yes. This provides good spatial coverage and good sensitivity. And this is typically referred to as a multi-receiver array. And this is the default operation mode on any clinical MR scanner. They can have up to 64 channels, typically clinically, and in a research setting it can be even higher. So each of the receive elements is attached to its own preamplifier and its own receive chain. Another reason that you want to go with this is to achieve acceleration, but that is for a different lecture. Okay, so let's say that we have like 4 RF coils. So as I mentioned, each of the RF coil is attached to its own preamplifier, and that is ultimately leading into its own digital receiver chain. Ultimately, you're going to get a signal out of that, but you don't want to just add these signals together for 2 reasons. One is that the phases of these signals are not the same, and so if you add them together, you're going to get phase cancellation. And then they also don't have the same amount of signal, so channels with less signal should be weighted less, and then there could also be noise correlation between the channels. So you need to have information about noise correlation, and then you need to come up with weighting factors and phase corrections to basically get these in such a state that when you add them together, you get the optimal combination in terms of SNR. So that's typically how multi-receiver array data is used. The actual weights, there are many papers on what are the best weights. There's multiple ways of doing that, but the result is always the same. You want to have the highest SNR summed channel data. Okay, final little niche subject is, let's say that you're interested in a proton and non-proton RF coil. So let's say proton and carbon-13 or proton and phosphorus. One of the better RF coils that you can use for that is shown here, where you have a proton surface coil, and then the X nucleus is a quadrature coil, where one element is 0 degrees and the other element is 90 degrees. The nice thing about this configuration is that for the proton, the B1 is primarily pointing downwards, whereas for the carbon-13 or X nucleus, the B2 field or its B1 field is primarily pointing horizontal. That basically means that the B1 and the B2 field are perpendicular to each other, minimizing the interaction between the two channels. This can also be done for human RF coils as well. Now, of course, this approximation of B1 and B2 being perpendicular is only a first approximation because there's many spatial locations where that's not the case, and so there will still be some interaction between the two coils. That is a potential problem if you want to do experiments like proton decoupling during carbon-13 acquisition, for example. So for those experiments, you will need to have additional filters in line. So here's the RF coil. Proton is in black, carbon is in red. The carbon coils are connected to a carbon-13 amplifier, and if you want to do carbon-13 decoupling, you basically want to have proton stop carbon pass filters. They basically leave the RF pulses on carbon-13 alone, and they can transmit as they need to, but they basically remove any kind of signal and noise at the proton frequency, so that is not directly transmitted into the proton receive element. Sometimes it's also beneficial that on the proton line to also have a proton pass carbon-13 stop filter, but that is kind of like depending on your exact scenario. But if you're interested in those experiments, definitely these kind of filters are going to be pretty important. So to summarize, I think RF coils are an essential part of any MR system. I mean, they're really needed for efficient and homogeneous RF pulse transmission. And then the same coil or a different coil can be used for high sensitivity signal detection. Because there are so many organs, frequencies and requirements, RF coil design is extremely diverse. Right? You have many RF coils, you have volume coils, you have surface coils and arrays, multi-element arrays. But despite all of these coils, there are a number of basic guidelines that you can use to get an improved RF coil. So you always want to minimize your electrical fields, especially your near field electrical fields, while at the same time maximizing the magnetic fields. Your B1 generation is most efficient when your RF coil Q value is the highest. So use high quality materials and maximize that value. Then of course it's important that the RF coil is tuned to the LAMO frequency and matched to the system's impedance, and that's why you have your variable tuning and matching capacitors. Now, this video only scratches the surface when it comes to RF coils, but I hope that this provides you with a few entry points to read further if you're interested in these kind of things. This is me, so if you have any questions about this or any other subject, come and see me at meetings and talk to me. You can shoot me an email, and some of these things are also available in this book, the third edition. Okay, thank you for watching the video, and hope to see you next time. Bye.